Zayed is the president of MBZUAI. He's a professor at computer science at CMU and founder, CEO, and chief scientist of Federated, a 2018 World Economic Forum technology pioneer company. That they build standardized AI development platforms and operating systems for broad and general industrial AI applications. His main research interests are in developing ML and statistical methodologies for solving problems including automated learning, reasoning, decision making, and so on. He focuses on dynamic problems in artificial, biological, and social systems as well. He's the reason why, he's one of the reasons why this workshop is happening. So I'm really grateful to for the opportunity.
I didn't hear what you said, but I'm sure it was elaborated introduction. Thank you for the introduction. Thank you for including me in this excellent, amazing workshop. Let me also spend a few words to wear my present hat and welcome you again. I hope you had a great night last night, either at the historical site or at a restaurant. So you can see we're trying very hard to build this new university, kind of a emerging center, for excellence of machine learning research. So you are literally our first batch of host, and followed by, of course, another 4 or 5 additional amazing workshops. But we have such a strong start. I really feel excited. I'm very thankful for Mike, Zayed, and all of you, to put together this program. Sitting in here, we actually also have some of our own faculty, so can take. In fact, the ML Deputy Chair, Kun Zhang, is also here. Feel free to catch up with them and learn about the school. And also, I think they are on a mission to attract people to join us. So if you have good students, colleagues, please do recommend them to our way. Thank you very much. Right, so I honestly, I feel humbled, to even be sitting here, standing here to speak, because in my current role, I don't really have the amount of time I wish to dive into deep research. So sorry for the superficiality of the material I'm going to speak about. So I've been making observations these 2 days, over the talk, and I was pretty impressed to actually learn many of the things I wasn't really aware about. But also I want to make some observations, right? So I found that many of the presentations and the focus has been on a very high level, or the meta level problem, where we're talking about the problem in designing the mechanisms of federated machine learning, the behaviors of learners, and also the way they interact and so forth. Right? But there is an elephant in the room that we don't really mention too much, which is what we actually learn. Right? The model, for example, that's the holy grail to learn. And usually we say some models. Basically, that's swept under the rug. Right? So over the past few years, if I was still kind of active in research, one of the things I did a lot is to actually build real systems. I worked with hardwares, with software stacks to really try to land many different machine learning and other models and applications to a workable state, pretty much like what Sana is kind of doing. And there are a lot of problems, more than just engineering. In fact, it also involves theory and principles and other things. Right? So that probably leads to what I want to speak about today, which is, I don't have a proper title. It's kind of together a few keywords, federated machine learning. And then I want to strike an issue on model parallelism. And okay, we'll see what I mean by that. And then, maybe a theoretical, maybe a principled approach based on variational inference, a thing I did many years ago with Mike when I was still a student. Right. So what is model? Well, this is something we might be building, in the industry, like an aircraft, right? But if you kind of take them apart, they are built like this. They have parts. And in particular, these parts come from all different places. In fact, they are manufactured in different countries. Well, that's a real example of a federation. We are really federating the whole process of aircraft prediction, right? And then, if we want to put the math on that, this is probably what's happening, right? So in every agent or every client, they build one part, but they probably are giving their material locally, but also they have informations, maybe from the central manufacturer assembly plant or from their neighboring plants and so forth. So big things are building in context, but into parts. And then, maybe at a central plant, they got assembled. And the way of assemblage is maybe to concatenate them or maybe screw them together. So this is federated production. You may find this approach very awkward, which is that, I'm going to build everything also locally, but in silo, I only take material from the local. I don't really know what's going on in other places. And then at the end of the day, I ship all my stuff to the hub and they got added, averaged, whatever, aggregated together into something like this. So what is this? Well, I guess this is probably the right way to build a graph. That's probably not something you want to do, right? But if we just map this practice, to machine learning, to federated machine learning, you actually probably see this more often. This is actually pretty much the spirit behind the FedF, okay? And also, common practice, which is a common practice, and also many algorithms alike. In fact, most of the algorithms I saw, most of the analysis I saw are already taking assumption, implicit or explicit, that this is what's happening. And I'm going to study convergence, stability, privacy, also the issues around it. And in here, that's actually trying to mirror what's happening in the federated production for the aircraft. What's happening is that, yes, you have the local information and you are using different local devices, but you have some context, either from the server or from the peers. And hopefully what's happening at the end is that you want to get whatever learned from the edge devices into here, aggregate them in a way that is not additive. Okay, that is probably either concatenation or maybe even more complex. So this is what I mean by model parallel. It is as a whole, the totality is a model, and then they got parallelized because the parts of the model gets produced in different places. All right, and I believe this is a scenario that is desired in many application scenarios. For example, we were working on a proposal to NASA, which calls for a solution to the wildfire forecasting. Well, okay, you put sensors in different places, and in fact, you can put them globally, and there are such systems, which collects, very, information from different continents, and they will assemble together. And you can imagine it's unfathomable to think about they are just going to average all this information, right? They have to be very, very locally specific, but also they learn things from other places as well. Well, even for other applications, just maybe in our core area of machine learning, well, I think this better. This is in computer vision, right? Alyosha had this paper many years ago called "What Makes Paris Paris." Well, it's because you have street scenes from Paris, you have street scenes from London, and how to distinguish these two city setting or the picture is that they have a very unique, feature maps or whatever, latent representations. If you start to add them together, you lose all these nuance. You have to basically build a very location-specific, or context-specific representations, right? Then for anything downstream applications of predicting locations and recommending paths and so forth. Okay. So that's basically the context of what I want to speak about today very briefly. Model parallelism in machine learning or in federated learning, where the clients are really training very heterogeneous models based on heterogeneous environment. And in fact, that's, I think, why we even need to have federated machine learning. If you have a homogeneous environment, you just use one sensor. You don't need to send drones or sensors all over the place, right? The reason you send those stuff all over the place is because they all see things differently, not a random sample from the IID distribution, but literally, a sample, maybe an independent or dependent sample from a different modality or parts of the bigger heterogeneous model. And then the server is to maybe concatenate all these subgraphs into a bigger one. And that comes to all the issues, right? So yeah, there are issues I'm going to raise, in computing and also in assemblage and so forth. So I said that I'm going to draw some wisdom and some insights from the older literature, in variational inferences. Again, I'm in no way to show off my knowledge in front of people like Mike, because he was really mentoring me, on that project. But these are basically, in fact, this is a figure, I published 20 years ago in the paper I wrote 20 years ago with Mike, on the generalized mean field inference. The idea is to break the whole thing into pieces, and then you introduce a variational approximation, which is a mean variational approximation, a mean field approximation, which amounts to product of disjoint marginals, right? You can make it a little bit more sophisticated by applying a best approximation to the free energy, which builds on, intersecting, overlapping, clusters of random variables. And that's already telling you that depending on how the original graph look like, your best approximation may be able to, converge the truth, or may never be able to capture the true distribution and so forth, right? So this is a big literature which has a lot of theoretical work and the practical implementations. But I think here are the key ideas that I think make sense or relevant to federal machine learning, which hasn't been systematically explored in my opinion. For example, I think that one key idea, in this type of variational inference is the idea of divide and conquer. You want to, break the bigger pieces like the model into disjoint or overlapping variable clusters. Then you define variable cluster marginals, which could be built as a submodels on every client. Subgraph approximation, how do you actually tie the parts together? It's a tree, or it's a more complex graph. That's another choice space that you can make. Then there is the algorithmic wisdom, mean field, LEP in loop-keeping propagation. EP are the names that were popular 15 to 20 years ago when people are trying to come up with practical algorithms to solve all this. Of course, at that time, distributed computing and clusters are not a fancy idea. So typically, you just treat one machine as if there are multiple cores, and then you just loop, linearly, sequentially, in the one machine. Then there are a bunch of theories, for example, the marginal polytope theory is helping to define the space that you want to optimize over. And the inner and outer approximation to this polytope is to tell you, what strategy you use, whether you want to choose, approximate, family of marginals, or maybe an approximate family, of loss functions. And then the choice of the loss function, like free energy approximation, becomes another constant. Right? So these are kind of the ideas that I can roughly, grab from the literature of variational inferences. Very rarely such ideas are actually used right now in federated machine learning, except that I found that this word EP was used. I'm going to mention that, but I don't think it's used in the way of its original definition. Okay. All right, so let's see, where are our fed learning paradigms, right? So I think we have, maybe this is a dominant paradigm, like the classical data paradigm. In fact, there's no difference between this one and a distributed machine learning. People actually oftentimes, at least at the system level, confuse FL with the DL. Okay, I couldn't really interrogate any difference, from a system implementer. What is that? Except that, in the DL, your clients is a box, and otherwise it is a iPhone, or maybe it's a, but when we saw experiment, you don't see iPhone being used either. Okay, you still see different machines. So in a sense, it's still difference. But I can tell you that when you actually get serious about the infrastructure differences, they cause a lot of trouble for you already. Maybe break all the theories and assumptions you make. And then, recently there are some work on variational technique for data parallelism. And today I'm going to speak a little bit about how to borrow this idea, extend it into model parallelism. Very quick, everybody probably know this already. This is maybe the most dominant application or practice of federated machine learning via distributed optimization. You run local SGD, you pass the outcome into the server, they aggregate, and you pass back the new one, and then redo the computing and so forth. There has been a huge amount of work reducing the amount of client computing, reducing the amount of communications, and also by imposing, encryption and other technique, MPC, for example, to do privacy preserving computing and so forth. So I'm not going to repeat all that. Now, quickly jump into a new paradigm, which leads to the inclusion of a variational inference technique, is that first of all, you started moving from estimating a point estimator of the theta into a posterior distribution of that. So you treat the problem of model learning as a posterior inference, right? And there are already a lot of versions. Once you have the posterior, which can be factored into a product of client-specific marginals, you actually capture the uncertainty of that estimator, which actually allow you to weight the importance of that estimation, that mean value. And also you may actually have a global covariance matrix which captures the dependencies between clients and all that. So it's nice to have such a thing, of course, not without cost. In principle, once you are in the domain of probabilistic posterior inference, you can now introduce a auxiliary function Q, and then you can factor them in the same way. And then the way you do inference is to turn them into a divergence minimization problem. You basically compute a Q that is the closest in KL or in other divergence to the true. And then that's basically a problem to solve, right? So this is only analytical. In practice, this is a very, very difficult problem. There are many ways of reducing that. In fact, one of the earlier reduction was very dumb, basically. This one can be kind of rewritten into a product of terms. Somehow the product of all the clients, that product operator can be taken out of the divergence function into a summation. And then this approximation, which is terrible, dumb approximation, now says that you can approximate this one with locally defined divergence functions, right? And then, in fact, that can lead to a one-stop algorithm that you just locally estimate this, through some kind of initiator function or whatever distribution prior, maybe flat prior, and then that leads you to a algorithm called the posterior algorithm. Obviously, this is not a very good approximation. So another idea is called now EP. In fact, it took me a while to understand why it is called EP, because it has to do with the EP I learned 20 years ago. But anyway, it is to really now elevate this back to what originally should be by introducing what this particular client heard from the server, a current version of the global model. And then I'm going to produce a cavity by subtracting that and then adding the local version back, make them look like the global kind of posterior, and then minimize divergence, right? So the intuitive idea. The ideas are very, very intuitive, but the implementations are actually all leads to the research because they are all very expensive. You need to worry about estimating local mean, the estimation of the local covariance, where you have 1,000 or million dimensional model. None of this is feasible both in computing and in communication if you are really working on an iPhone, right? And then there are a number of papers talking about all sorts of approximations, eventually bring them down to almost like a gradient-like step, which requires a delta of the mu. And what that delta is, well, it's weighted in a certain way and it should reflect local uncertainty. I'm not going to dive into that. But steps on the client side are taken also to reduce the computing of that. You can turn a full estimation into a SUV-based and CMC-based sample from a surrogate function. And then you can compute both the mean and covariance using some additional tricks. One of the tricks is a linear complex to the dimension, even in computing the covariance or the inverse of the covariance matrix. So with all these tricks, you can see that this algorithm, even though it is not a very good approximation to the original KL, it is already leading to a much better kind of a convergence in terms of accuracy and also the speed, comparing to the posterior averaging, to even estimating a Gaussian mixture. Okay. In fact, some of the algorithmic tricks are substantial in terms of speeding up the conversion, as see from this black curve, which is based on, I believe, a MBZUAI. And practically, you can see that it applies very well on even non-trivial neural networks, of CVAR 100. And in practice, we burn in, the MCMC with the iteration with Fed average. And then at some point, we jump into Fed posterior average, and then you can see the improvements. Okay, so that's PA. A few more words about EP. Well, the reason I say this is that this is not what I wanted, but I'm going to use it, for the model paracomputing. So in here, the computing at every client and also the server become a bit more tricky. It involves introducing a few stepping stones, which are respectively called the cavity distribution, which basically is the global minus the local, and then reconstructing the tile distribution, which is the cavity adding the local, the newer version local back, and then you need to approximate with a easier parametric form, such as a Gaussian or a Laplace approximation. And then you need to compute the delta so that they become more like an incremental addition. And then you're going to incorporate. So all these steps involves the choice of the variational family and additional tricks for client-side inference, which I'm going to speak a few words about. Adaptive optimization, which allows you to use more tricks like momentum, like proxy or approximation and so forth, to smooth the trajectory. Stateless and stateful kind of trade-offs, how much memory you want to keep, or how much indexing or a variety you want to keep in the whole cohort. Imagine you have a million client. Well, in that case, you don't want to keep a million states, or these are the kind of practical issues. So yeah, so usually choosing version family is the simple thing. We like Gaussian. We usually go with a Gaussian approximation. We take advantage of the natural form where you can basically do addition, some simple operation primitives over updates. And these are the steps the tricks people typically use on the client side. They're using stochastic gradient, MCMC, using some simple approximation to the complex distribution, and maybe sometimes even to forget about stochastic computation and do natural gradient variation. You just take the bound, the M-ball bound, and take a gradient. So all these can be used, and then here are some typical steps, where the updates, can have additional adaptation step, such as, as I mentioned, gradient and so forth. And stateless clients, as I said, if you run into large number of clients, you don't want to really, deal with, 1,000 K. You can either cluster them into a smaller, or you keep a global client, which is a very, very kind of a silly trick, but it actually worked many times in practice. Yeah, so here I have some comments on EP. I really don't know why it is called EP, because it feels like the later authors were not aware about the literature, so they kind of view message passing to be generically an EP algorithm. I'm running out of time, so I'm going to quickly jump into, there are some results showing you some improvements even over FedF. But now let's go to where this talk is about, model ML. So in here, the idea is that on every client, I want to keep a part of the model, or focus on a part model, maybe destroy the parts. But symbolically, they actually has a expression that is no different from what I saw before, right? Basically, every part is a submodel, but here there is a complement that which can be kind of pushed down, into through a delta function, so they disappear, okay, like this. Okay. You can also, in practice, people found that completely letting this go is causing the local client to lose the context. Therefore, you may want to use some kind of a quantizer to bring back some information as the context to include the inference. But in fact, I don't need to say too much now, because if you look at this particular equation, it is actually similar to the FedEP equation I just used, which was focusing on parameter. Here we focus on the model structure, which is also just the parameter, which is the weight of the graph. So okay, so that's basically a thought I want to share. In fact, depending on how you context them, by bringing in the context, And the sparsity basically is a way to show that how I partition, the clients, to have a share of the model. You see, the more you break your model by using high sparsity, you lose some accuracy, but you can bring back some accuracy by having a good quantization step to bring in more context. So this is looks like it's working. Another type of model, in fact, I didn't say what this algorithm is used for, what model, right? For example, here I have another model which is also of interest, a mix of X models, another old kind of thing that now becomes suddenly popular because it turns out that you can use large data to train a gigantic mix of extra models, and then for very generic functions. But how to train? In fact, it's almost like a perfect fit for federated machine learning because experts correspond very nicely, to clients. Therefore, you don't have to do very ad hoc partition. But in this case, you need to also make sure that the clients have a contribution to learning the gate function, which is actually a global thing. So then what's happening that in the server, you need to get information back as the subgraph or the subnetwork, and also the gate function they integrate. And obviously there are some difficulties in the cost, right? So this one is a big one. So one idea that we found to be interesting is that you can actually locally estimate not only the expert network. Remember, Mike, the other day talked about uncertainty quantification, for example. That actually could be a practical tool to even help the server to determine which expert to use, in terms of how trustworthy it is, right? So I can actually estimate the uncertainty of the expert network locally without using the other information. And that actually provides a way of gating mechanism, which hopefully can be more cost-effective. Of course, how to do uncertainty estimation is itself, it could be an expensive thing because one of the ideas we use is to just explore a number of dropout models to see how the application or the performance degrades, right? And then you can accordingly weight, but that means you run the same task multiple times, which is expensive. But practically, it does improve the results quite substantially, over say a Fed average idea of a mix of experts. Another idea we also find to be very useful, and then in a minute, is allowing further sharing between the clients. That of course needs to be decided on what to share, what not to share. Well, there are some information which are surely shareable. For example, feature extractors, say if you are doing computer vision, right? And that means maybe a few layers in the local experts are amounting to just a very high level feature extractors, which can actually be shared across all clients. They might be trained in a Fed average or whatever data parallel scenario. But then this unique finer elements of the expert network has to happen locally. So this basically now becomes a combination of a model parallel and the data parallel scheme for training mix of expert models, which we also found to be kind of a quite useful. It actually improves empirically the accuracy over a standard say network quite visibly. And also you can now measure the accuracy over the number of clients and see your opportunity to incrementally increase the performance just by adding more resources into that. So that's basically where I want to add. I have some slides on privacy, but I think we all know that we don't have to go through. There are some limitations and some open problems in terms of really still how to do better uncertainty estimation on every client, and how to cover like the capacity and the computational burden, communication overheads, and so forth, which I thought to be interesting, maybe topics, for theorists and also for algorithm people, system people to study jointly. Okay, I think I'm going to end here, just some very, very high level ideas. Thank you.
Any questions?
Yeah. it's very interesting, the variational framework that you propose for federated learning. And I was thinking about the cavity distribution that you have with the P. And so I was thinking, like, doesn't this kind of provide some natural framework to define also personalization? Like, since at the end, locally, what you're estimating is the complement of the cavity. So it gives you a natural way of expressing the specificity of each client respect to the rest. So I don't know if you've thought or elaborated around this concept. Also, for the privacy perspective, the fact that the cavity clearly exposes actually.
Yes, yeah. Indeed, these are just the beginning of the study. We now are in the state of getting things work. So we introduced the cavity and also the tiled, just to make sure that the whole thing gets the correctness. And then, once we have that, in fact, the next step we did is just to, again, worry about the computing, the approximation and the computability of that. Privacy has been studied a little bit now by using the MPC idea, but here the MPC are not applied to data, but to the model parameters. We actually don't want the clients to steal model from the clients when they are prompting. In fact, nowadays, this business of prompting the larger models becomes an enterprise. And there is a risk of large companies to lose asset. So yeah, there are this type of study, but I don't have any formal kind of results on that. It's all very ad hoc at this point. All right, thanks a lot.